before it goes online. Okay, now we are going online. Let me see how many people here. Okay, we have 16 users here, so I think we have sufficient number of the audience already. Then I think we can proceed to our first presentation. The presenter will be Nikita, and the paper being presented will be modeling functional similarity in source code with graph-based seamless neural network. So I'll hand it to Nikita.
Thank you everyone for joining for the talk. So I'm Nikita Mehrotra, PhD at IIIT Delhi, India, and today I'm going to talk about HOMES, a code clone detection tool based on paper modeling functional similarity in source code with graph-based Siamese neural network. So it was accepted for publication in TSC last year. Code clones are code snippets that are similar to each other. These snippets can be similar in terms of program semantics or syntactic structure. Semantic similarity implies similarity in behavior. So, for example, if program 1 multiplies two integers in the multiplication operator, its semantic clone uses repeated addition algorithm to multiply the two numbers. While syntactic similarity can be in terms of program syntax and structure. For example, the similarity between program 1 and 3. This is an important problem and a lot of work has been done in the past few decades. This graph shows the number of problems related to code clones from 1999 to 2021. Code clone detection can help in other software engineering problems as well. For example, in code refactoring, bug detection and program repair, for code reuse and etc. Although a lot of work has been done to detect code clones, but detecting functional similarity is underserved, and we identify challenges with the current techniques. The first challenge is the use of syntactic features like AST program tokens for modeling functional similarity. And the second challenge is the choice of neural network like simple feed-forward network or LSTMs that destroy code structural, semantic, and syntactic features while learning high-level program representation. So to address the identified challenges, we proposed a code clone detection tool, HOMES. This figure here gives the overview of code clone detection pipeline. It takes as input program dependence graph of the code pair and it passes it through a graph-based weight shared network to learn code representation, which are then compared using a binary classifier. So HOMES is based on two key insights. First, feature plays an important role. Thus, to model semantic features, we make use of program dependence graph representation of the source code, which encodes program control dependence and data dependence information explicitly. And second, to capture program semantics encoded in graph structure of PDGs, we make use of graph neural networks. Now I'll explain the representation learning framework of HOMES. The code snippets are first passed into program dependence graph, from which node feature graph adjacency matrix are extracted. The are then passed to a attention-based graph neural network, which explores the depth and breadth of the graph adaptively to learn high-level program representation. And to explore and capture the long-range dependencies existing in the PDGs, we repeated this process of GNN, and in each iteration, GNN explored different top neighborhood for a target node. Next, we pass node feature vectors to JK-net architecture. It is similar to a ResNet network to incorporate and aggregate node feature vectors from different iterations of GNNs. The final learned node representations are then passed to a tension-based graph pooling layer to learn representation for the entire graph. Now these learned high-level program feature vectors that output from the graph pooling layer are passed through a binary classifier which measures the code similarity. To evaluate HOMES, we use dataset from programming competition and open source Java projects. More details about the dataset are presented in the paper. We used TBCCT, a tree-based convolutional neural network code clone detection tool, as a baseline, and we aim to answer two research questions in this study. In RQ1, we compared the efficacy of HOMES against TBCCT, and in RQ2, we aim to assess the generalizability of both the tools. So our results of RQ1 demonstrates that Homes outperforms TBCCD on both Google CodeJam and BigClone bench dataset. On dataset, both TBCCD and Homes performed equally well, while on the GCG dataset, we got an improvement of around 10% as compared to TBCCD. And the results of RQ2 demonstrates that Homes generalizes better on unseen code snippets and projects when compared to TBCCD. So, based on the study, we can draw some implications. First, the comparative results between TBCCD and Holmes shows that semantic information that through PDGs is useful for measuring code functional similarity. And second, GNNs can better capture programs' syntactic and semantic features as compared to other traditional neural networks like convolutional networks or LSTMs. So, thank you all for attending the talk.
All right, thank you, Nikita. I think we'll move on to our next presentation. Revisiting process versus product metrics, a large-scale analysis. So I think Tim will present.
Yep, thanks for the introduction. I'm reporting the work of my graduate student, Suvadip Majuma, who's now working in industry for summer. Why talk about process metrics? Why talk about different kinds of ways to look at code? Well, I think we have to look at a different fundamental shift in what we think software engineering is. Once upon a time, we might have thought that software engineering was all about some mathematical process where theorem provers inputted requirements and output code. But now it might be more accurate to say that we think the code that comes out is a function of the whims of people and how they work. So instead of just looking at code by what the code's built, let's ask about how it's built and what we know about the people. So we're talking about product versus process metrics. So product metrics are things like lines of code, inheritance, the sort of measures we see when we extract code. Process metrics over here are things like, have you touched the code recently? And what's the experience base of the person that touches the code, et cetera, and how you're dividing the code up into directories. Now, one interesting thing about process metrics is that they're language independent. If you do product metric-based analysis, you have to keep changing. You've got a problem mapping inheritance-based languages to non-inheritance-based languages, et cetera, et cetera. Process metrics can be applied, and product metrics are a real problem when as it is in current projects, many projects contain mixtures of code in different languages. So the process metrics, being language independent, are very attractive. Now, process versus product has been explored before, but not at such a large scale, like the ICSI 2013 paper by Ramal et al. About process versus product metrics was quite a good study, but it dealt with just a few projects. If we look at recent literature, recent top SE venues, and say who's talked about product metrics and who's talked about process metrics and who's actually compared them, and there's not many of them. And then if we ask how many of these have actually, used more than 10 projects to do it, and so the whole process versus product metric is ripe for revision given larger information. So we looked at 700 GitHub projects. We extracted product metrics with the understand tool, process metrics with GitHub Commit Guru. We didn't do feature selection. We did do some rebalancing. We looked at file level versus package level prediction and didn't find much difference between those, by the way. So per project for cross validation, we'd do a 5x5, or for release-based planning, we'd learn on the past and predict on the future. And then we do hyperparameter optimization to tune some of our choices. And then we ran a bunch of learners and we collected the usual performance statistics. And then we analyzed them with non-parametric methods to look at effect size, blah, 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 blah. Okay, on to the results. The blue are the process metrics. The brown are the product metrics, and the green is the combination of both. So process beats product if the blues are higher than the browns. If the blues are higher than the browns, and they are, the blues are higher than the browns. And for false alarm, the blues are much lower and better than the browns. Another thing we noticed for if you're reasoning over 700 projects, it's really useful to use a committee-based analysis method like random forest. Notice how random forest, the variance in the conclusions is much less than if we go to logistic regression or naive based. So from here, we're realizing that if you really have a lot of information sources, use multiple models, because single model inference it gets confused by all the information. Multiple models can average out across them. We find no benefit in combining product and process metrics. The green, which combines both, isn't anywhere different. We also find no benefit in, say, going beyond random forest to, say, deep learning. If we're getting, PFs approaching 95, 98%, recalls 95, and false alarms getting down as low as this, there's not much benefit going on. On other measures, area under the curve, we had the same pattern, process beats product. And for things like POP20, we found it uninformative for working out which one was better. And so conclusion one, use committees when reasoning about lots of data. Don't use single models. And conclusion number two, process metrics are really cool. People build software, and the way people build software is one of the key determinants of whether you get bugs in that software. And then I've got some related work and ideas for the future, but I better stop there. Thank you for your questions. Thank you for your time.
Okay, thank you, Keith.
Am I the next talk?
Yeah, I think next talk is still will be presented.
So please join with me in thanking the speaker, and let me introduce the next speaker. The next speaker is Tim Menzies from NC State, who'll be talking about learning recognizable static code warnings. Okay, now the thing to note about this paper is it's wrong. It is completely wrong. It is utterly wrong. There's a really great ICSI 2022 paper that shows all the conclusions of this paper were based on incorrectly labeled data. All the conclusions of this paper were based on incorrectly labeled data. Okay, folks. So if you get your paper refuted by an ICSI paper, what do? Do you go home and cry? Or do you sit down with your critics and say, what can I do? What can I do? Okay, so that's what we did in this paper. So I'm not going to present the paper. I'm going to present what we did when we found we were refuted. Now, the problem is static code warnings. You've all seen screens like this in FindBugs where some static code analysis tool has told you that the null value is guaranteed to be dereferenced or something like that. And if you've got the same tools I have, you spend a lot of time ignoring the warnings that come out of these static code analysis tools. In fact, nearly all of these warnings are routinely ignored by developers. So this was studied previously by Wang, and they had some data sets which we used in 2 papers. And then Kang et al. Came along and said, guys, you've got 30,000 records. There's data corruption errors in 29,000 of them. 29,000 out of 30,000. But Kang et al. Couldn't take their corrected data and produce good defect predictors. They don't have very good precision and recalls. So we took their data, and in working with them, we asked, how can we produce good predictors for static code false alarm warnings that should be ignored using their data? Now, what we found is, and there's a lot of information on this slide, is we found his precision near 100%, AUC near 100%, false alarms, there's no blue here, down to nearly 0, recall up here at 100%. We found that in collaboration with our critics, the people who refuted us, we found a bug in how people reason about software engineering data. If you look at how people build the hyperspace boundary between examples, it's usually based on global decisions. So if you're doing support vector machines, you can tweak the hyperspace boundary using parameters like this. And what we've realized is that's a mistake. We're getting much better results not by making global decisions about how to shape this data, but by making local boundary decisions. The methods we recommend now go to specific parts of the data, and in that local region, we decide how to oversample and undersample and how to build a little hill just here and to push away the boundary in that region. Now, it would be an entire another talk to describe to you those methods. So I'll just motivate you to look at them with the following diagram. This is the decision boundary before we do the smoothing of the boundary. And there's lots of maximum complications. And this is the decision boundary after we do our global tuning, when we find the world is smooth and nice. External validity point. Please note that in the smoothing operations we're doing here, we do it on the training data. We do not touch the test data. It's a threat to validity if you smooth the training test data. The test data should be as it is. So we're talking about things like boundary engineering, label engineering, instance engineering, and we've got methods for doing that now. And that's in a preprint. And if you send us a request, we'll certainly send you information on that. But I think you're going to hear a lot more in the near future about boundary engineering, label engineering, and instance engineering. So what happens? What should you do with critics? If your work is refuted by another group, what should you do? Well, this has happened to me several times in my life. The more papers you write, the more chances you get, critics that refute you. The thing to do at that point is to realize that people critiquing you are the people that know most about your work. They're the ones who think that what you're doing is worth exploring. They're the ones who can offer you most insight. Your enemies are your friends. So we don't have enemies, we have collaborators. If you ever get refuted by someone, lean in and ask them, can we work together to get better results? And the next paper that shows us how to improve on the 2022 paper will have all these people as co-authors, the original developers, the people who refuted us, and we'll all get together and try and get a TSC paper together. Okay, thank you for your time.
All right. Thanks, Tim, for very good presentation and the lesson learned. All right, so next presentation will be improving the learnability of machine learning APIs by semi-automated API wrapping. And Lars will be the presenter. I'll hand it to Lars. Lars, you are muted.
So yes, I am. I just had to unmute myself. So thanks for the introduction. My name is Lars, as was already mentioned. I'm a PhD student at the University of Bonn, and I want to present now our ideas about improving the learnability of machine learning APIs. As a case study, we have taken scikit-learn, which is a very popular machine learning library. The reason we chose scikit-learn is on the one hand because it covers a lot of different ML tasks that come up. So supervised learning, unsupervised learning, etc. And because the API of scikit-learn has influenced many other machine learning APIs, so the results that we have here can also be transferred to other APIs later on. First thing we did is just have a look at how large scikit-learn actually is, because if we can reduce the number of API elements in there, then we can already improve the learnability because the things that people actually need become more visible. And we have found the numbers indicated by those red bars over here. And I just want to highlight the number of parameters down here at the bottom, which is over 4,300. So conclusion here is it's a very large API. Afterwards, we had a look at Python programs on Kaggle, the website for machine learning competitions. And we found around 42,000 programs that were actually using scikit-learn. And using this information, we then checked which of the API elements of scikit-learn are actually used by at least one of the programs. And those are the used elements that we have defined here. Results are that out of those 43,000 parameters, only about half of them are actually used. So the other parameters don't offer any benefit to any of those 42,000 programs that we've analyzed. And for the parameters, we can also go one step further and only keep useful parameters. And we define those by a parameter that is set to at least 2 different values, because if the parameter is set to always the same value, we can just replace it by this constant value, which leads to another slight reduction in the number of parameters that are actually needed in the API. So overall, we can get rid of 57% of them. Afterwards, we had a look at the remaining parts of the API and checked whether there are any problems with usability and learnability that we can still get rid of. And I just want to highlight one of the problems here. It's very basic to keep the presentation short, namely the use of strings to encode enumerations. This is something that has evolved in Python over the years because it didn't have specific support for enumerations initially, and it didn't have it when scikit-learn was first introduced. So instead, many Python libraries and scikit-learn as well chose to use strings instead. So then you have a string parameter, but essentially only the 5 values that are listed here, linear, poly, etc., are actually allowed as possible values. That has a couple of drawbacks. You always have to check the documentation to find the legal values. It's hard to detect any typos statically. And it's also hard for IDEs to offer any auto-completion because while the documentation by now has some sort of semi-formal syntax, it's still not as formal as proper type annotations would be. And the solution in Python is now to use the enums that have been introduced, as well as possibly type-ins, which allows us to just formally define the type of declarations in the language directly. And that basically gets rid of all the problems that we had with the initial approach. And moreover, we can also keep the documentation shorter and just focus on the description of what a parameter in this case actually does. So now we have some existing library, in this case, scikit-learn, and it might use, for example, the strings instead of enums here. We cannot really change this library directly because it already has a very strong user base. People know it, people like it for very good reasons. So what we want to do instead is create some wrappers that internally uses the functionality that scikit-learn offers, but to the outside offers a better and improved API. As in this case, we could have a kernel parameter which now has a type int, the kernel, and which now uses enums instead of strings. So now the question for us was, we have a library and we want wrappers around it. So how can we get there? Because as we mentioned, it's a very large API and we don't really want to do this tedious work by hand. So our approach is instead to first of all parse the existing library, get some API structure definition out of this, which is some higher level abstraction than source code, sort of like an AST. Afterwards, we take this API structure, put it into an editor. There, the user can add what we call annotations, improvements to the API, such as saying, okay, please replace this kernel parameter over here, which is currently a string, by a proper enum. We get some annotated API out. Afterwards, we have some inference layer, which gives us an improved API, and we put this into a generator to give us the actual wrappers around it. And the important bit here is that the only part that the user has to do is to enter annotations in the editor, and we're also in the process of automating this for many of the annotations that we support. So with that, thank you very much for your attention, and yeah, I will hand over to the next presentation then.
Thank you. So our next presentation will be about improving machine translation system by isotopic replacement. And our presenter will be Zeyu Sun. So Zeyu, I will hand over to you.
Yeah, thanks, King Miss Queen.
Yeah.
Yeah, thanks. Hello, everyone. I'm Zeyu Sun from Peking University. This is our paper, Improving Machine Translation Systems via Isotopic Replacement. Machine translation is able to translate between thousands of pairs of languages effectively in real time. The tools such as Google Translate and Bing Translator are widely used in people's daily life. Such machine translation systems are not perfect, and the bugs that users experience have a different character from those on traditional non-machine learning-based software systems. Recently, quite a few approaches have been proposed for testing machine translation systems. To test this system, a promising trend among those approaches is to use word replacement. For example, given the sentence, "Women do good research in computer science," a testing approach transfer can generate test the sentence by replacing the word "woman" with a similar word "man." This input sentence is further paired with the original sentence as the test input. Then, the testing approach feeds those two sentences to the machine translation system. Since there is only one word exchanged in those sentences, their translations ought to be similar to each other. In this example, though, there should be only one word differences between those two translations. However, if the translations are not similar to each other, the testing approach reports it as an inconsistent bug. Those approaches are good. However, precise control of the impact of word replacement in those word replacement-based approach is still difficult due to the full semantics of natural language words. For example, the word "great" in this sentence is not suitable to be replaced by the word "good." To tackle this difficulty, we propose a novel word replacement-based approach called CAT to machine translation testing. Given a sentence in the source language, CAT performs isotopic replacement to generate new sentences. And the goal of isotopic replacement is to control the impact of word replacement. To realize this as topic replacement, we first conduct context-aware word replacement, which replaces a word within a sentence with another word that is also suitable for the context. Then we calculate the context-aware semantic similarity between the original word and the replace word and use this similarity to discard the word replacement that influences the semantics. Following a testing and repair approach trans-repair, CAT can test and further repair the inconsistency bugs. This is the overview of our approach. In this paper, we focus on 4 research questions on the effectiveness of test input generation, bug detection, bug repair, and the efficiency. We conduct experiments on 2 machine learning translators, Transformer and Google Translate. Since CAT follows transpair, we select transpair as the baseline. For the effectiveness of test generation, for each sentence in our dataset, we generate test input with CAT and transpair, and we found that CAT generates nearly 10,000 test inputs, while transpair only generates nearly 5,000 test inputs. For bug detection, CAT detects 129% more bugs than transpair. And for bug repair, CAT repairs twice more bugs than transpair. For efficiency, CAT is significantly more efficient than transpair in mutant generation and bug detection, and has comparable efficiency with transpair in bug repair. To conclude, we propose CAT, an topic replacement-based approach to improving machine translation. And the experimental results on Google Translate and Transformer show that CAT performs better than transpair. That's all. Thanks for listening.
All right, thanks Zoe for your presentation. So next will be our last presentation, which is also a paper-winning Distinguished Paper Award. The paper title is Collaboration Challenges in Building Machine Learning-Enabled Systems, Communication, Documentation, Engineering, and Process. Our presenter will be Nadia from CMU.
Thank you. Can you see my screen?
Yes, we can.
Okay. So hello everyone. I'm Nadia Nahar, a software engineering PhD student in Carnegie Mellon University. So this is I'm presenting the paper titled as Collaboration Challenges in Building Machine Learning Systems. And I hope you have seen the longer version of the presentation. And if not, I hope I can at least make you interested to look into that. So I always like to start with this example. When thinking about a machine learning system, we often think of a notebook where we can write some code to train a model and get some output of the prediction in some form. So for example, this is a face detection model that detects human faces images. Now, this face detection model is not an application or product in itself, but if we want it to be used by end users, it may be embedded inside a photo app as a component, which will look something like this. So now this photo app does not only contain the machine learning model, it has many more components along with the model. The machine learning face detection model is only one component of this entire system. So for building this kind of system, we need many different roles to work together. So there might be a group of data scientists who we can call as a model team who will be in charge of the machine learning model. There might be software engineers in charge of the other engineer pairs who we can call as a product team. And there might be a data team for managing data and many other different roles like managers, domain experts, and so on. So now talking about such projects, we find many articles that talk about that a large number of data science projects never even make it to production. And among the issues, we find the problem of lack of collaboration in different forms that leads to a lot of problems. So we felt that it was important to look deeper into the boundary between disciplines because that's where a lot of problems seem to be. So this led to a research question to find collaboration points and challenges between different stakeholders, especially software engineers and data scientists. So it was a qualitative study where we conducted 45 interviews in 28 organizations. It was a 4-step process to come up with the theory. So I'm not going deep into the methodology due to time constraints. So this is what we came up with. There are three major collaboration points where the interviews were facing most of the challenges. So here you can see there are some subcategorized topics and some icons beside the topics. These are basically the themes around the collaboration challenges, as you can see in the bottom of the slides, and you can also find it in the title. So now all the companies doesn't face all these challenges of all these themes based on different team structure, working style, and different different team combinations. They face different challenges. So I'll show you one example of a challenge from the requirements collaboration point. So in this collaboration point, the primary collaborators are the product team and the model team. The client and the management are also involved in shaping these requirements. So suppose this organization named Organization A has a banking software, and now they want to detect fraud in that existing software. So the requirements for this company flows in a way like this. The management and the product team first comes up with the product requirements, and then the product team talks to the model team, transferring the product requirements to the model requirements, and the process goes on. So we categorize this type of organization as organization of product first trajectory, because the product was developed first, and then they felt the need of a model which came later in the process. The problems that this kind of company faces is when the product team comes up with the requirements with the manager, they do not include the model team. As a result, they come up with requirements that might not be realistic. For example, the product team might decide to detect all the frauds in the product, but we know that machine learning is not capable of providing 100% accuracy. So now when the product team talks to the model team says that it is not possible for them to build such a model. So it creates conflict between the product team and the model team. And also, as this is very late in the process, the success of the product is put at stake. So as you can see, we found two themes of collaboration problems at this point for this organization. One problem is the problem of communication because of not including the model team during the requirement process. And the second one is documentation, because we have seen that often the product requirements are translated into model requirements verbally without any written document. So this elevates the conflict of the two teams more. As a recommendations for mitigating the first challenge, we recommend to input data scientists early during the requirements gathering phase, not afterwards. And for the second challenge, we recommend to maintain documentation for both product and model. So as you can see, I showed only one challenge in one problematic topic. There are many more challenges that people face in these collaboration points. And as you can see in the themes, a lot of the challenges can be mitigated with better communication and documentation and emphasis on AI literacy and education. And we also need to appreciate engineering effort more to make things, this kind of product successful. And also there is a scope of research in defining good process for this kind of machine learning systems. So I hope you read the paper and get to know all our findings. So due to time constraints, I cannot go deeper into these challenges now, but I will be more than happy to discuss about this afterwards. So in summary, collaboration problems can lead to failing machine learning products. So this is an important topic that we need to put more emphasis on. From talking to 45 practitioners in the industry, we figured out these three main collaboration points that need special attention. And we also try to provide some recommendations based on the industry best practices and existing tools and techniques of software engineering. So thank you.
All right, thanks for all the speaker for their presentation. So next we will dive into the Q&A session. Let me see in the chat if there's any question. Okay, there are multiple questions, so let's go through them one by one. I think Tim asked a bunch of questions. First one, let's talk about. Can Tim let us know which paper are you trying to ask for your question?
Well, the first paper, I was wondering about finding clones, and then what would happen if you say that they're similar, but they're actually not. But then as soon as you showed your results with really high F1 scores, I wondered if you actually had enough. But is there anything you can learn from the false alarms where you say things are similar, but when you look at them, they're actually not? And you might say no because you had so few of those, because your F1 scores were so high. Nikita.
Okay. So yeah, it might be possible. So like it's possible that we might get a large number of false positives, and if we explore those false positives, we might get some useful insights like why this model is failing, or what extra information that we can so that we might reduce the percentage of false positive and the number of true positives can go up. So yeah, it would be great if we explore that space as well.
All right, I see Tim has another question about similarity.
Well, I actually want to throw to Lars because it sounds like Nikita has a comment that there might be an overlap between literally all our work. Like Lars is editor, modifying things. Nadia's talking about communication challenges. Nikita's doing clones. Like, what if Nikita's clone stuff was applied to Lars's stuff to help Nadia's errors, for example? So, Lars, do you have a comment on that?
I mean, in a sense, I think there are very similar tools you have to apply on the one hand to detect codes and on the other hand to detect the defects that might occur. So rather than checking, okay, whether the code is really the same, you could use maybe the same idea to detect a given pattern in the code. So for example, for us to do this automation of the annotation detection, we are also in this case using Spacy. We're currently using some rule-based pattern matching in Spacy to figure out places where, for example, this enum case occurs. That could also be replaced by neural networks and machine learning. The reason we are not doing this right now is because we need training data for it. And once we create training data for scikit-learn by hand, then we could just as well implement the wrappers around scikit-learn by hand. So currently the approach is to use this rule-based stuff, but I think there could be some potential overlap to really find places where improvements could be made.
I actually have a follow-up question on that one. So, how your tool, I mean on Lars, so how your tool would adapt to the software evolution? For example, what if some unused API become popular due to certain changes, or some popular API become unused due to certain changes? So how your tool would adapt to those kind of evolution in the software or API usage?
We haven't implemented anything yet, but the idea is that we basically run a diff between the API structure that we have. So currently this is some JSON data that we get out, some representation of the AST, compare it with the old version of the library with the new version, and then figure out what the additions and changes were that actually happened there. And is there something in the background? Okay, I'll just continue. And then we would basically take all the annotations, so those improvements to the API that apply to the old version, and also apply them to the new version as long as the API element is still there. So we can take all that stuff with us. Whenever there are changes or deletions in the original API, that might be a different story, of course, because then some of our annotations might become invalid in the case of changes, and some of the annotations might have to be deleted. I mean, if an API element is outright deleted, it's not much of a problem, then we can delete it as well. But we always also have to keep our target audience in mind, because we don't want to break the code for them either. So it's a bit of a tricky question there, what sort of changes to the original API we also want to propagate forward.
Yeah. So I noticed Tim has a bunch of questions. Which one you want to go first, Tim? Like for the rest.
Anyone else? Anyone else ask a question?
Okay. So let me see. I think so. You ask a question to Nikita. So
Yeah.
you want to illustrate your question a bit?
Yeah, I have a question that have you ever tried some pre-trained models like Colbert?
So have you tried any pre-trained model like Colbert
Yeah.
for your work, Nikita?
Oh, no, we haven't tried it yet. But yeah, I mean, we can try that. But I don't think pre-trained model will work in that case because our input is very different. I mean, we're constructing PTG, so we might need to change a bit at the input part to get it work.
Yeah.
But I think then heavyweight model as compared to GNNs, so it might require a lot more compute resources than GNNs. So that is another challenge. And then, like GNNs, as said, they consider or exploit the similarity program structure. So let's talk about PDG. So the different edges of the PDGs, like control edges or the data edges, denotes different information. Like using GNNs, we are able to exploit that information. So that is advantage of using GNNs over transformer.
Yeah, thanks.
I've seen Tim ask many questions, so I will ask some questions to Tim's work. So about your process, so it's great to see that it's a language-independent matrix. So have you considered about such matrix works for development of machine learning models? Because we know that machine learning models is not just about language itself, right? Sometimes it requires some type of hyperparameter tuning, this kind of task. Will the process metric also work on that type of software development?
Well, we've done an awful lot of hyperparameter optimization, and that's typically an algorithmic based approach. There is a kind of process we're thinking about recently, and that's the process of dispute. If you've got developers arguing over something, or if you have a part of the code being revisited a lot, and another process metric that's very interesting is the change, revert, change again. So are there ways to identify the hot spots that Lars' stuff needs to fix using my process metrics, for example? You know, this I think would be very interesting. But I would suggest to you all that, look, I mean, if you know the stuff I've been doing, you know I'm a great fan of automation. Okay, but people build code, or people package code, or people propagate code. So let's study everything everyone else is doing in this session. Absolutely. But let's also study the way developers interact and how that critically impacts on things.
Yes, that's a really good suggestion. I also noticed that the product metrics based on your reported results is really poor. So do we still have any value to use the product metrics? Should we just abandon the product metrics at all based on your results?
When you go to repair, you're going to need product.
Okay.
Like if you look at the people doing program repair, you know, they're absolutely fit. I mean, anyone who's parsing an AST is doing a product metric. But you know, I really think it's not either or. I think that there are cycles. Nadia is talking about the sort of ways, you know, large things mess up, large repair strategies. Nikita's telling us where, if we fix something, we should also go to the fix. And GU is offering us an incredible heuristic. You know, small changes to input should lead to small changes to output. Otherwise, you've got a problem. You know, so I think I can see a wonderful combination of everyone's technology.
I see. I also have a question for Zeyu's work. So since you asked a question, let me ask you the question back. So you talk about this semantic similarity concept, but how do you identify the core semantic of a sentence? Right, for example, for different tasks, for different NLP tasks, let's say, right, like entity relation, extraction, the entity actually will be very important, right? But for sentimental analysis, the sentiment would be really important, right? But for translation, I will see both entity, sentiment, or other component could be important for the translation. So how do you identify the core semantic here? For example, I change men to women. I substantially change the entity itself. People could argue saying like you also change the semantic, right? So what would be the so-called core semantic in your paper?
Yes, thanks. This is a good question. And we just computed the semantics use BERT, and the BERT is trained from many tasks, many data, and it can compute the semantic vector, and use this vector to represent the semantics of the sentence and of the word, and we use this BERT vector to measure the semantics and compute the semantic similarity, and we have checked many examples, and we find the semantic similarity is the BERT computed is really good.
Okay, so now you mentioned you manually check the semantic.
Yeah.
Then is there any guideline for you to follow to say their semantic are similar or not? Because I guess different people would have different opinion in that process, right? In terms of whether the two sentences have same semantic or similar semantic.
Uh, we select similar words like woman and man, and corresponding words like good and bad. Sometimes it is similar in a sentence, and yeah.
Okay.
Thank
So
you.
your main ground truth would be relying on human to decide. That's what I understand. Okay. All right. So I also see an interesting point raised by Tim's presentation, second presentation, which kind of matching the theme of the last paper, which is the collaboration, right? So I'm not sure whether you two want to comment on this, like in terms of the suggestion Nadia gave in her presentation or in her paper about collaboration, and the collaboration team just some suggestion team just mentioned in his presentation. You two have any comments on each other's work?
Yeah, I can also see one of Tim's question in the chat where you were asking whether Lars' model. I can see any collaboration challenges in there. So I can point collaboration challenges in all of these works. So you see, when you build a model, there's we cannot just let the model provide the model to the users and ask them to use it. So we have to provide some wrapper around it, so some engineering spurs where the user can interact with the model in some form with some other engineering features. So maybe a button to click on the model, like ask, okay, give me all the code clones like the work Nikita that did. So when you're building such a system, you need some software engineers to build that system, because that's the engineer pairs the data science might not be interested in. So I have one specific collaboration point where I found a lot of issues is the integration of this model and the system. So when the data scientists and the software engineers are directly collaborating to build that entire product. So in that part, I found three types of collaboration patterns, how they generate. So there was one where the it's called model as API, where the data scientists will just deploy the model themselves and provide an API to the software engineers, and the software engineers will just use that API. So then there is a model shared code where the data scientists will provide the model code directly to the software engineers and ask them to deploy it in some form. And there was another kind of team where it was all in one. So there's one combined team of both software engineering and data scientists, and they're working together to deploy the model and build the engineering parts. So for these three patterns, I found very different challenges that these people face. So for the first pattern, when the model is deployed as API, so we are expecting the data scientists to deploy that model themselves and know the engineering pipeline and know how to deploy those stuff and provide it to the software engineers. And I have heard complaints from data scientists that they don't want to do that. So they're not there to work on the engineering parts. They just want to build a model, do the explorations and those. So there was one collaboration challenge in this part. Then when you provide a team where you can just the data scientist doesn't just share the code to the software engineers, there we found issues that software engineers are complaining about the code of data scientists. So you're providing some model files, and it often happens that the software engineer completely rewrote everything in that, and when they're deploying that model, they're not getting the results that the data scientists were expecting. So there is an issue on that collaboration pattern. And then again, when you combine all of them and provide in one group, in all in one, so there they have complaints about the boundaries between the responsibilities. So they're saying that, okay, I don't know which part I'm responsible on. There is no task divided well enough. So yeah, there is a lot of complaints on that part. So I haven't found any ideal situation to break this thing. So it always seems like a good idea to make them communicate between themselves a lot more than it's usually happens. So there is a problem of siloing of data scientists when like it doesn't matter if they're in the same group or in other groups. It always happens that the software engineers are working together and they're just communicating with the data scientists to get the model part and then integrate those. So this creates a lot of problem. There is a problem of different expectations from the code quality. So there is no common ground where everyone says that, okay, I'll follow these code patterns for both these types of systems. So yeah, there is a lot of issues on in these different parts that I have seen in the industry. So yeah, I don't know what team thinks about that. What do you think?
So
Well,
I
Okay.
have
I'd like.
sorry. So I just have two follow-up questions. So can't we have a plug-and-play kind of architecture, and we have like things defined for a data scientist and things defined for an engineer to do their, just provide them with a plug-and-play kind of architecture where they just put their respective code and things will work. So can't it be possible?
Yeah, so yeah, in my work, I'm recommending a lot on the engineering part like that. So because if we can provide some established infrastructure for both of them, so it might happen that they can come to the same ground based on those automated architecture. So yeah, that can be a good way to solve this. But currently, there is no like common frameworks that they can work on. There's not even a common process that they can work on. So yeah, maybe that can be a good potential area where we can provide some simple steps or some automated frameworks to them, and where they can just yeah, follow up with their work later on and set on common ground, common assumptions based on some documentations and so on. So yeah, that looks like a good way we can try it.
And can't we have like a similar or same software quality metric for both the like both the set of codes, or is it like for the data scientists the software quality metrics are different as compared to the engineering part? So what's the difference between the two, or
Yeah,
is it possible to have similar?
yeah, there is a lot of quality concerns actually. So the code quality is very different. Even the vocabulary is very different for these two type of people. So if you just think about some simple terminologies, that for example, if we talk about performance, a data science understand that I'm talking about accuracy. And if you say performance to software engineering, he understands, okay, it's a response time. So they don't even have a common vocabulary to work on, and let alone the code quality. So yeah, the
But
software engineer.
performance, no, I was just saying, but performance is something like data scientists also try to optimize their code so that the training burden is minimum, and so there are work going on to minimize the code.
No,
I
no,
think
I'm
you're right,
saying that
Nikita, that there are common concerns, but I think it's also important to talk about the uncommon concerns. The data scientist might be more data centric than the developer, who might be more code centric. When I try to work out how my learners are doing good or better, I sometimes look at code, but it's far more productive to look at the data,
exactly.
landscape analysis on the data. And so the thing about you can't, it's very hard to do invariance, for example, on a machine learning algorithm, because the learner has outputs that's the product of the learner and the data coming in. So there are very different concerns.
Hmm.
And
Yeah.
if I'm talking different concerns, I really want to push Nadia on this point.
Mhm.
She's talking about connections between technicals, data science,
Mhm.
computer scientists. What about the community leader who's talking to the data scientist and saying, I don't want your systems to discriminate against African Americans in my system. So now you've got people actually with fundamentally different goals. The data scientist might want to be cost effective, get the model out as soon as possible. The community leader might want to be, risk aversive, or might be worried about empowering. Like, do you have anything on that, Nadia, or is that
Yeah.
a bridge too far so far?
Yes, no. That's to clarify that I'm not only talking to people in the technical part. I also talk to a lot of people in the non-technical part. So the project managers who talks to the data scientists. And there's a lot of complaints on AI literacy in that part because the data scientists often feel that the project manager is not understanding them because as I give the example of that 100% accuracy. So it's very common. So I think more than 70% of the data scientists that I talk to say the common concern that they cannot make the project managers and the clients understand that they cannot have 100% accuracy on a single task. So it's very hard for them to set expectations from the non-technical users, and it's also a problem of project management perspective where you have to set some timeline to deploy a model. So project managers, like in software engineering process, we always have some concrete deadlines and timelines. Okay, we have to fix this thing within this time. So in data science, as it's the exploration process, so you cannot say from before that, okay, I need 1 month to finish this model, because you don't know. After exploring the data, you might have a good understanding. You might know that what the accuracy can be in this perspective. So the project manager have trouble understanding these concepts. So they're having trouble understanding that they need to have some extra timeline or something else in the data science process so that the data scientists can work on the exploration parts before just implementing the model and providing something. And there's also a lot of problems on training data, as you were saying, in data-centric approach. So the clients and the project managers often find it hard to understand how much data the data scientists need. They often provide a lot of data as well, but the data are not in good quality. So the data scientists say that I cannot use this data to make a good model. And I have also heard complaints from data scientists that a client have come with an Excel sheet with 20 rows of data and asked them to build a model on that. So these are the cases that happens in the industry when the data scientists are talking to a non-technical users who doesn't have a data science background. So this is why some of the recommendations we have is to conduct some training sessions early before just approaching the project, just sitting with the clients and the managers and telling them that, okay, so for building this model, I will be needing this support with the data. I'll be needing this time for exploration and so on, so that they can at least have the same assumptions and expectations as the data scientists.
But be careful, my distinguished colleague. When you talk to disenfranchised groups about what happens when technicals arrive, it's not like if we open the pipe, we'll understand each other and get to a common place. There is the situation where people actually have different goals.
Yeah.
So one of the great myths of the 60s was if we all hold hands and hug, we'll all come to a common world. And one of the beautiful conclusions of the 21st century is that we are different and that we should respect those differences.
Exactly.
Yeah.
So like they don't have to have the common goals. At least they have to have set the common assumptions. So at least they assume the
Wow,
same
even that. Oh my God.
Yeah. Yeah. So yeah, I'm thinking more about like setting something that everyone can agree on. So if even if you're different, like if you are building a system, you should at least have some agreements that the
All
system
right.
is going to work like that.
So take a policing system. Okay. Well, we had the Fairware conference on Monday, and we learnt about the forensics people whose fundamental mindset is they need to help the prosecution make their case, which is not a statement of we need to find truth about who's guilty and not guilty. Okay, so
Yeah, exactly. Just realizing that it's not about.
I think your studies are needed, but It's a hard problem.
I know. Yeah, that's why we need to be more careful in this. Like, yeah, that's why we need to think about these parts. Like, as you said, it doesn't have to be that you agree that if your goal is to predict if someone is like just true or false something. At least you agree on the part that we are not.
Well,
Our goal is not that. So at
well,
least we
let's
have the
let's
same.
let's 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 go back to Lars. Okay, now let's say everything Nadia and Nikita's talking about is working, and let's say Jiu's found us our bugs. So now your people have to fix things, right? Now, what's the effort involved? Like, what's the cost model for your people using your tools? Like, I take it you haven't refactored all of scikit-learn yet.
We are in the process of doing so right now. Yeah. So
So tell me how long it takes people